if you get a job, for example, paying you $60,000 or $70,000 a year, and you probably don't want to go back to graduate school because for a master's program, a lot of times you have to pay for the tuition yourself. So you will be getting like $60,000 a year, and then you get into the master program, you'll get zero because you have to pay for the tuition. And they may have some scholarship to pay you back, but eventually the balance will be pretty much zero. And if you get into a PhD program, you don't have to pay anything, 90% of the chances, and they will pay you somewhere around $20,000, $30,000 a year. You'll be fine, but compared to $60,000, $70,000 a year, it's a huge difference. And if you already have a mortgage or a car loan or something else, or still paying student loan, you cannot afford all these things anymore. You have to sell your house, sell your cars, it's total pain, and go back to graduate school. So I would rather just spend another, I would do the PhD anyway, because you'll never see that ceiling anymore. Just get it done in 4 years and then start looking for jobs. If you really don't want to become a PhD, I think the master's is fine, but you have to be able to, pay for all these tuitions. Financially, have to support yourself, I think. So let's look at a clocked circuits. So I'm going to use transmission gates to form D flip-flops instead of using gates. The reason I want to use transmission gates is because it takes way less space compared to the TI D flip-flop. So let's look at the level trigger circuit first. Level sensitive. Latch. Start with the latch. It's a level trigger flip-flop. Still remember the schematic of the TID flip-flop? So many gates in there, like AND gates, OR gates, or NAND gates, and that's just a one flip-flop. And you have to use, if it is a 64-bit digital system, you need a 64 of that, and that's just for one counter. So it scales up really quickly. That's why you want to consider some of the other structures like this. So first, this is a level sensitive latch, and this is on the CMOS book. It's figure 13.21, and it's on page 386. So here's the schematic. It's clock, that's a PMOS. The reason that this is a level triggered latch is because there's no second stage to control the signal to be sent to the output. And that's a combinational logic. And definitely this inverter is being powered up by VDD. So whenever the signal is being sent to this point, it's going to be directly transmitted to here, to the output. So whenever the clock is high, D will be sent to Q. That's why it's level triggered. So what is this part doing here? And why not just use a transmission gate as a D flip-flop, right? Whenever the clock is high, all the signals will be sent to Q. Why do we need something like this? Yeah, it's a latch. It stores the signal, but how? This stores the signal. This latch is being controlled by this clock, and the transmission gate is nothing but just a switch. So whenever this is on, the circuit is equivalent to this. And that is the latch. Keep in mind, whenever you see this, you want to tell people this is the latch. And you may see a different form somewhere else. In SRAM, for example, we're going to introduce it really quickly. What's the difference between these two circuits? Are they equal? So if I draw it like this, that's an inverter, and this is going to here, this is going to here. Are they the same? They are, right? What about these two? Yeah, if you merge, like look at these two wires, I mean just shrink it and make it like this. And these two, just reshape it like this. And this is being shorted to the output of this inverter, and this is being shorted to the output of the other inverter, right? So the input of this inverter is being shorted to the output here, and the input of this inverter is being shorted out to the output of this inverter. Same circuit, same schematic. And that's going to be a latch. And why is that? Just look at this circuit. It's easier to figure out why this is a latch. I'm going to redraw it here. Why this is a latch? Because the inverter has a switching point, remember? So if this is the input, and this will be the output, and that will be the voltage in-out curve for the inverter. And if you draw the input signal as well, it's going to be linear line for the input. So that will be the switching point, right? And for example, this is 2.5 volts ideally, if this is 5 volt logic. So the only way it's not being, so the signal here and here is not VDD or ground, is to hold this point perfectly as 2.5 volts. So it's not doing anything. So it's not triggering anything. It's just 2.5 volts for both. It's just stabilized at this point on the curve. It's not moving to anywhere. But whenever this is larger than 2.5, what's going to happen? Yeah, so this will be high, and this will decrease quickly to 0. And whenever this is decreasing, it's even making this larger. So this start going up, like going to 3 volts or so, and even higher because this eventually will reach 0, and this will reach 5. So what's this called? No, you have to have an odd number of inverters to form a ring oscillator, but this is not. This is a latch. Whenever you see this, you just want to tell people this is a latch. It's not, is it stable? No. I think it's pretty stable because you can, ideally, it is 2.5 volts, then it's going to be held at this point, in the switch point, at the switching point, but it's not possible in real life. Any little noise will trigger the change, and it's changing to the two extremes. It happens quickly and then being stabilized over there. So it happens quickly. whenever you power it up, since you have powers for the inverters, right? Now connect all the inverters to the power, then it's going to happen. It's going to be either this or this. It's called positive feedback. Positive feedback. Because it's just making the case worse. And whenever this is a little bit higher, it's going to lower down this voltage, and then it's going to make this even higher, and then lower, then higher, and then just like this. Positive feedback, right? So it works for the other way as well. Either this or this. So that's the latch. Because it's going to help that value like this or this, depends on the input. So you have a D as an input. If this is 0, you are going to have a really stable 1 here. Right? Even 2.4 is going to trigger a 1. But you got a 0. Right? It's going to be a very stable 1. Right? So that's why it's a latch. It's going to hold that value really steady. Sorry. Yeah, thanks. So this is a level triggered D flip-flop using a clocked circuit. And now let's see a edge triggered version. Q, that's Q naught. And clock. So why this is edge triggered? Here's D data. So what's happening here? So keep in mind, so these two TGs, did I draw it correctly? No, sorry. These two should be the same. These two should be the same, and these two should be the same. Right. So this one and this one should have the same clock signal to trigger. And these two are the same. As you can see, clock is controlling N modes, clock is controlling N modes. So whenever, for example, when the clock is going low, so these two will be turned on. At the falling edge, what's going to happen? This is low, because whenever this is low, this TG will be opened up. So D will reach here, but not here. Because whenever this is on, this is off. Let's label it as A. Is that correct? Whenever at the falling edge, D will be sent to A. because this is off, so A cannot reach Q. However, this latch will be activated because these two has the same clock signal. So whenever the data is being sampled, when the data is being sampled at the falling edge, the data will be stored at A, and at the same time, the previous Q will be latched here. So it's holding the previous value. And then it's going to be held there because this low signal will keep this latch open. So it's going to be a memory. And at the next rising edge, A will be sent to Q. Right? So the question is this a falling edge triggered or rising edge triggered? Rising edge, you just look at when the data is being updated, right? That's a rising edge. Any questions on this? No? So let's look at the digital model for the transmission gates so we can analyze the time delay for these flip-flops. Are the resistive and capacitive digital model for TG's transmission gates, RC resistive and capacitive digital model for TGs. So let's draw the transmission gates and see how we can model it for digital signal analysis. That's C load. That's a load capacitor. That's a transmission gates. Is there a Miller effect taking place whenever the signal is being sent to the next stage? Is there a Miller effect taking place? So in order to send the signal to the next stage, you have to turn it on, right? So we assume that we are keeping these TGs on now. When this one is being sent to here, is there any mirror effect taking place? C load. So what is mirror effect? Remember? So whenever you are increasing the voltage of the capacitor on one side, and on the other side, you are pulling it down to the ground as well. So 0 to VDD. At the same time, you do it from VDD to 0 on the other side, right? So you have two sources to do it. But now this one, for this case, it's just one source. Just one source, one signal is being sent to here. If this is high, this is high. If this is low, this is low. Right? So there's no mirror effect. So the capacitance here will be simply a half of Cox P. And here as well, a half of Cox N here. And the same for all the other ones. So these are the capacitors. What about the resistance, the channel resistance for these guys? you got two channels in parallel, so the channel resistance will be in parallel as well. So the model looks like this. And here's a C load. This will be Rn in parallel with Rp, and all the Rn and Rp values are given. And these will be the same R and same Rs and same Cs. And what about the capacitance in this model? So I just simply converted everything here into this guy. So what's the capacitance? Whenever I'm looking at the time delay, I'm just looking at the output. So here is a capacitance by looking into the output to the left side, to the left-hand side. Then this part will be, you got two capacitors, two or one. So we got one here, right? So it's going to be totally Cox P plus Cox N. So this one will be, and they are all equal, except for the C load, which is given by the customer. All right, so this is how you model it. And now let's look at the clocked DFF, how to calculate the time delays of that circuit. And that's on page 394 of the CMOS book. We just take this input part out from this model to analyze the time delay of this part. That'll be this. And resistor, inverter, another inverter. So we keep this on. Remember which ones has the same clock. This one and this one and these two. So when this is on, these two are off. Right? So when it's off, you don't have to look at its caps. It's not doing anything to the circuits. So that's off, off. This is on. So looking at this part, you got a half of Cox P here. For here, what is this? A half of Cox N. I got an inverter. So the inverter's input, you got two caps. So what's the C in of the inverter? The input capacitance. C in. For the PMOS, what's C in? Remember all these caps? So what is the overall C in? For P, let's do P first, right? 3/2, right? So because this is Cox P, has a mirror effect. This is a half Cox P. It's going to be 3/2 Cox P. 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 3/2 Co This one, 3/2 of Coxswain. That's all for this point. If we name it as A, point A, so these are all the parasitic caps for point A. Whenever you are looking at the time delay from D to A, you just need to look at the time delay, the capacitance at point A. And here's point B. So what about point B? What are these parasitics of point B? Because there will be definitely there's a mirror effect here, which is Cox P. Another mirror effect cap, which is Cox N. There's nothing to this one because it's off. And also this point is being shorted to this inverter as well. So there will be one here, one here. That's the input. That's a C in. So C in has 3/2 of Cox P, and this is 3/2 of Cox N. All right. So the question is estimate the delay from D to A and B. D to A, D to B. And the parameters are given like this. NMOS Rn is 3.4K. Cox N is 0.625 femto. For PMOS, Rp is 3.4K. Cox P is 1.25 femto. So let's get the capacitance at point A first. So what is CA? CA will be these two plus these two. These two plus these two, right? These two plus these two, which is a half Cox N plus a half Cox P plus 3/2 of Cox N plus Cox P, which is 2 times Cox N plus Cox P, right? Yep. Which is 2 times 1 point, just as it's two together, is 1.875 femto, and we're getting 3.75 femtofarads. That's the overall capacitance at point A. So what about CB? What is CB? CB is these two plus these two, these two plus these two, which is Cox N plus Cox P plus 3/2 of Cox N plus Cox P, which is 5/2 of Cox N plus Cox P, which is 4.7 femtofarads for the calculation. So delay from D to A, delay from D to A, whenever you are being asked to do this, always look at the output. which means whenever you are trying to figure out the time delay from D to A, you're looking at A. So TPHL equals to TPLH. The reason is it's just the same gate. It doesn't matter it's going through which transistor. It's always running through the parallel channel resistance here. So this should be equal to each other. And which is 0.7 Rn in parallel with Rp times Ca, right? Because it's from D to A. So always look at A. And this is, let's just do the calculation. Ca is already calculated. Just plug in all the numbers in there, right? And you're getting somewhere around 4.5 picoseconds. We haven't done all these calculations, just want to save time. So just want to make sure you guys are familiar with femto and pico, right? Pico is 10 to the negative 12th. Femto is 10 to the negative 15th, right? Don't forget that. So what about delay from A to B? From A to B. And always look at the output. It can be different because it's passing an inverter. It's different from the transmission gate. So the transmission gate is being modeled as the parallel resistor of R and RP. So it doesn't matter is TPHL or TPLH is always running through this resistance. But in the inverter, it's different because from A to B, it's running through an inverter. Actually, two inverters. So TPLH is which type of transistor is taking effect? LH, which one? LH is PMOS, HL is NMOS. So I have to calculate it separately. So TPLHB at the B point, which is 0.7 times what? R what? No, A to B, are looking at point B. So point B is being shorted to inverters, not the transmission gates. And why this one doesn't have the channel resistance, since it's being shorted into the input of the inverter? Yes, of course, it's being shorted to the transmission gates, and we model the resistance to be the parallel resistance of the channel, two channels, right? But also shorted to the input of the inverter. Why we are not taking care of either RN or RP for the rising and falling delays? Why is different compared to here? So right now we are looking at the time delay for the point B, right? And we're saying, hey, the rising, whenever this point is rising, the current is running through the PMOS. So we need to use the RP to calculate the time delay. It's 0.7 RP times CB. Whenever we are calculating TPHL, it's from high to low. So it's discharging the point to the ground. So RN is running the current through it itself. So we should use 0.7 RN times CB. But why not doing it here? Because this is also being shorted to the inverter. Why we are not just using RP or RN, but rather we are using this parallel resistance, not the individual ones. So how did you model the input of the inverter? Remember, right? It's disconnected. So it's not going through the RNRP. So only the output has a connection with the resistance, but not the input. So we don't have to worry about the RNRPs. So only these two resistors are conducting currents, but not these ones. The channels are not doing anything here. Only the input capacitance are doing, contributing to the time delays. So here from A to B, and we are doing LH, we should use RPO-RN. RP, yep. Which will be 0.7 times 0.4K times CB. So what is CB here? This one. Into the calculation. It is 11.2 picoseconds. And now calculate TPHLB, which is 0.7, since it's HL, so you are using RN, equals to 0.7, 0.4K times, still the same CB, 0.7 femtofarads. It's just the same value because R and RP are the same. Which is great. So whenever you are designing the NMOS and PMOS, you want to make the channel resistance to be the same. But however, the resistivity of the channels are different. That's why we size the dimension of the PMOS and NMOS differently. You know, normally we have a larger PMOS and smaller NMOS. That's why the PMOS and the NMOS are different in terms of the width. So now let's get to the conclusion. Since we have calculated the time delay from D to A and also A to B, so what about the time delay from D to B? D to A, you have these, and A to B, you have these different time delays being separated or calculated them separately. So you just want to do it separately. So it's going to be TPHL equals to, they just use the same value because these two are the same. These two values are the same. It's going to be 4.5 picoseconds plus this one. HL, right? This one, 11.2 picoseconds. Um, 15.7 and TPLH is this one, 4.5. Yeah, they have the same values, but in case if I give you a different RNRP in the exam, you just need to know how to calculate it. It's going to be this LH, the first LH plus the second LH. 4.5 picoseconds plus 11.2 picoseconds, which is 15.7 picoseconds. Same values. So we are done with digital models for CMOS. Any questions by far? No? So the homework 5, is it homework 5 or homework 6? Homework 5. Homework 5 is due this Friday. And that's the last homework assignment you are going to have. And homework 6 is teaching evaluation. And then a project report. And one lab report left, and a final exam. Then we're done for the semester. We have 10 minutes. Let's start the topic of memories. So there are some of the acronyms you have seen online or somewhere else. Just write it down and see if you know what are they. SRAM, DRAM, SDRAM, ROM, Flash. So one concept, the first concept, volatile or not. Which one is volatile, which one is not? So these are volatile, and why? So if you disconnect the circuit from the power supply, you'll lose everything. So what are the full names for these things, these acronyms? Yeah, so these RAM is random access, right? DRAM is dynamic RAM. SRAM is static RAM. And we'll look into the circuits and see why it's dynamic, why it's static. And SDRAM. So what is SDRAM? Since SRAM is static, DRAM is dynamic. So what is SDRAM? Static dynamic. It is not. So it's a synchronous dynamic. So SDRAM is still a DRAM, but an advanced version. So which is being used for the cache and which one is being used as a card out of the chip of the CPU. So let's draw a table. Probably that will be a better way to summarize everything on a table. So it's just mainly SRAM, DRAM, right? So these are all DRAMs. SDRAM is also DRAM. DRAM is also DRAM itself. So SRAM and DRAM, and they are being used for different purposes. So I shouldn't have this column, but never mind. So SRAM has less power compared to DRAM, and SRAM is faster compared to DRAM. So it's being used for the memory for the cache in the CPU. And SRAM is insensitive to noise. And also SRAM is used inside the CPU chip. For cache. And it's normally 20 to 40 nanoseconds to read or write. And it's normally a 6 transistor circuit. For each memory cell. Yeah, compared to this one, this is less power, is definitely more power, slower, It's not instant. It's not. So this is more sensitive to noise, and this is used off the chip. So normally it's the cards, right? It's a memory cards you can insert to the motherboard. And the response time is 60 to 100 nanoseconds. And it has transistor and capacitors. A little bit more compared to this one. But normally just one. For each cell, it's just one transistor and one cap. That's how I compare this two. So when you are trying to order a DRAM online for to expand, to upgrade the RAM memory for the computer. So there are all different names: DDR, DDR3, DDR4. Right now is DDR5. So all these versions. I did a search here. So let me see what are the years for these memories. So for DDR means the double data rate. They're all DRAMs, right? Double data rate, SDRAM. So you can directly buy it online. And DDR was launched in 2000, and DDR2 is somewhere around 2003. DDR3 is 2007. DDR4 is 2014, and DDR5 is the most recent one, is 2020. And for example, 16 gigabytes DDR4 SDRAM, you can buy a direct order from Amazon. The cost is normally like $60. So the main players, the major players that make SDRAMs, for example, Micron, definitely need to know. Where is Micron? Boise. And Samsung and Hynix. So these are South Korean companies. And what about Kingston? Have you bought any DRAM from Kingston?
Mm-hmm.
So Kingston is not a IC manufacturer. They just have a company and buy all these ICs from either Micron or Samsung and assemble them on the PCB and sell it. So Kingston is not a memory designer. They are just a vendor, I guess, or just a PCB maker. So these are the three major players on the market who make all these memory cells. Still have a few minutes, and it's definitely not enough to run all these circuits. I'll just call it today. Is there anything due tonight? Not, probably not. Next week, right, for the lab? All right. See you on Wednesday.